The second most popular question that you've asked on the forum is, why do we make so much effort to construct quantum repeaters if there's also post-quantum cryptography? So first of all, let me emphasize that we build quantum repeaters, or a quantum internet, not only to run cryptographic applications. So, of course, quantum communication is very useful for quantum key distribution, but this is only one of the many things that we can do using a quantum internet. Nevertheless, let me go back directly to your question, and let's compare quantum key distribution to post-quantum cryptography. So first of all, there's already some basic differences that relate to the security guarantees. First, quantum key distribution is a protocol where, on paper at least, one can prove that even an attacker using a quantum computer cannot break the system. Quantum key distribution, it is what is called information theoretically secure, which means that the attacker doesn't have enough information to even start breaking the protocol. Post-quantum cryptography is a computationally secure scheme. It means that one relies on certain computational assumptions that are difficult to solve for an attacker. So the attacker in principle has all the information, or a significant amount of information, about the key, but because this information is, if you want, encoded in a difficult computational puzzle, it might take me a long time to get back to the key, namely as much time as it takes me to solve that puzzle. So already here they're fundamentally different. In one case, the attacker doesn't even have enough information, so you can give him any computing power that he wants and he cannot solve it. In the other case, the attacker does have that information, but has to solve a difficult puzzle. And it's assumed that that puzzle is difficult. So it's important to understand that these are only assumptions that these puzzles are difficult to solve. In fact, a lot of classical crypto as we use it today on the internet relies on unproven assumptions of how difficult it actually is to solve these puzzles. But you can also imagine that because it's a puzzle that I need to solve, eventually, even if I need to wait for many years, I might be able to solve it and then learn the key and the secrets. So depending on how sort of long you want your secrets to be safe, you can make a judgment of what's sort of best for you. This actually brings me to the second very important point when comparing these two schemes. Namely, you might say that they're sort of trying to solve exactly the same problem, but they're not. So the use case of quantum key distribution in practice is, I think, very different than the use case for post-quantum crypto. So quantum key distribution enables highly secure point-to-point encryption generation of a key that can be used in a, say, symmetric encryption system. Post-quantum crypto is maybe less secure, so the kind of security conditions are much less that can be obtained using this highly secure quantum key distribution system, but it also has different use cases. For example, you might also do public key cryptography. In practice, I actually think that these two will not be sort of an either-or decision, but rather that they will sort of go in hand to hand moving forward. For example, one might use public key cryptography to bootstrap the authentication in quantum key distribution. That only needs to be secure for a tiny amount of time, namely before we initially made key, thereby allowing more people to do quantum key distribution without a priori negotiation.